Okay, hi, I'm Mike Siddons. Has anybody seen this product here? Anybody know what this is? Okay, what is it?
Huh?
What do you think it is?
The heat pump.
Yeah, okay, it's a solar boosted heat pump, yeah? So this was originally called the Solar Plus. It was developed by Siddons Ramsay and Melbourne University. Back in the 70s, the original ideas were sort of developed for a solar boosted heat pump. So the idea was to run refrigerant through panels that were mounted on a roof to absorb solar radiation to improve the efficiency of the heat pump water heater. So that was the original idea. I got involved in the company after it got spun out and privatised in the early 90s. And I was a Victorian sales manager. Then an opportunity came to run the business in New South Wales. And so I moved to New South Wales to run the factory in the mid-90s. Now, don't laugh, that's me. So that's the original air-sourced quantum heat pump water heater. And these things actually really took off during the 90s and then later in the 2000 period, and they're still going strong. The idea for it was to be effectively a plug-and-play solution. So, at the time, there was a lot of complexity wrapped around the whole hot water heat pump sort of design configuration. The air source heat pumps were large. They had heat exchangers that were causing a lot of problems. The solar boosted heat pump that we had needed 3 trades. It was an absolute nightmare. So I thought, okay, let's go with a kind of really simple little solution that you can put on an EcoFlow manifold, and you can kind of expand it out as you choose. So I originally did the R&D with the help of Kirby's Refrigeration, who are now Heatcraft and no longer manufacturing here in Australia. But they were great, and so on a very tight budget, we came up with this basic design. The design itself has what they call a condenser tank, and we got rid of the solar boosted configuration, so no longer did we need to run refrigerant through these black panels on the roof. There was a little fin coil in the compressor assembly area. So what you're seeing there is a compressor assembly that you would find in a normal refrigeration unit or an aircon unit. The hot refrigeration gas, once superheated, passes through the condenser coil. The coil itself is effectively bonded to the tank, so the heat has nowhere to go. The tank itself is insulated, it's got about an inch of insulation, so the heat's got nowhere to go except for in the water. And actually what happens is that you increase the surface area of the heat exchanger, but the amazing thing about the design is that it takes away any issues to do with scaling, which is something that plagues all heat pump water heaters. It takes away issues with pumps and controllers and so on, because it's a basic mechanical thermal system. So it has the ability to sort of control itself. So you see here, this is the condenser tank. This is the refrigeration. It's bonded to the outside skin of the water heater. The water heater heats up, heating the water inside. It also had another interesting feature, and that is that it had some really good thermodynamics, because the tank itself would heat the water would come to the top and then sort of drop down in the middle. And so you get a really nice sort of thermal mixing, because obviously it's hotter on the sides and cooler on the middle. And I used to have all these perks when I was doing the job. I'd go to Fiji. I actually stayed at the Sheraton in Fiji, and it was completely free. I said, I'll go over and inspect your water heaters. We put me up, and they go, yeah, no problem. And met these Qantas stewards, and we went out in these flying boats, and it's great fun. But we got one of the heaters, and we cut it in half. And this heater was on one of the islands, and it had literally a stalactite coming down the middle where the anodized where I can't say it, where the anode, that's what I'm trying to say, where the anode in the middle was. So the anode itself had done its job. So all the minerals in the water, and this was an island, so it had a lot of minerals. All the minerals had accumulated on the stellartype to be a stellartype, and the tank itself was completely clean. So the system actually worked brilliantly and had worked brilliantly for 10 years. In fact, the reason we cut it open is it had some rustings, some other parts with the TX valve and so on. And the guy was interested to see the health of the system, so we just cut it open and had a look, and it was quite amazing. So it was the only water heater in existence that could work on these islands in Fiji. It used to heat up in about 2 hours, or even less. That's 340 litres, and it was only using a 1.1 kilowatt compressor. So really amazing COPs. So what this is about is the reason that I became passionate with heat pumps, and I think this next 2 slides kind of gets to the point. Solar is really efficient when it's sunny, you know, but when it's not sunny, solar obviously isn't efficient. And the trouble with hot water heaters is that it's counter-cycle. So what's actually happening is that when your hot water load is at the most, your contribution from solar radiation is at the least, the amount of also the cold water temperature is at the lowest, so your delta T's are higher. And so what actually happens is that the top curve is your load. The next curve, the green one, is the efficiency of the heat pump. And now what's happening is that it appears that the heat pump is becoming more efficient in winter, but it's actually not, because if you look at the distance between that curve and here, it's more. So the reason it's being dragged up is because the load is effectively dragging it up. It's consuming more energy, it's producing more energy. As with solar, it drops away rapidly. And this is the sort of the fundamental problem with solar water heaters. So they work in summer really well, but they always struggle in winter, you know. Now, I'm not saying there's not a space for solar water heaters. I'm not saying that at all for all the people who love solar water heaters. So they're a great product, but let's not. So now, I thought what I'd do here is I've got some slides. I got invited to this conference on solar cooling, and I'm going to reintroduce this theme at the end of this presentation, and I'm going to throw out an idea for a new product, okay, or a new concept, and I'll be interested to see what people think. It's not, I don't think it's patentable, so it's really just an idea. So I'll challenge the audience. So Graham Morrison, who you probably all know, I'm assuming, former Professor of Engineering at Sydney, New South Wales. So he had these slides, and I'll just show you some of them. This is going back into 2010, so as a historical document, it's kind of interesting to see where we were then and where we are now. So you've got your traditional solar water heaters, like Solar Hut made famous. In the next slide, you can see the quantum heat pump that I've already showed you. And you've got a nice little cutaway of the condenser tank there, so you can probably see that a little bit clearer. And the next slide is a larger commercial system with some gas, some heat recovery, and these are the kind of more engineering-oriented solutions that I'm sure some of you are familiar with. So this is a nice little photo here of the original Solar Plus, which was the solar boosted heat pump. And you do still see these around. I've been seeing these water heaters going for 20 years. 20 years. So a heat pump water heater without any problems, still going for 20 years. And but when they originally came out, there were R12, you know, which is so good these days. But so the refrigerant's just going through these panels, and the panels get cold, hitting the tank. Well, the panels don't hit the tank, but the refrigerant does. The last slide is after we sold Quantum. we developed a new company called Sidon SolarStream, and the idea there was to use a larger evaporator. So I went over to China and did some work with Shigo in China, and got them to basically reconfigure some of their air conditioners to our design, and we used their air conditioner effectively as an evaporator, and the condenser tank was as per the original Quantum one. Okay. So this slide, you can see some trends for solar heat pump sales in Australia. So it's a fairly significant market. It's a market that experienced a lot of growth up to about 2010, although the growth has subsided a little bit since then. And in recent years, the trend is now back on course, and there's been a pickup in heat pump and solar sales. So this slide is interesting. I'm sure a lot of people here are involved with solar PV, but if we go back to 2010, it seems like a million years ago, but it's not. And you can see the impact of photovoltaic at that time was pretty much tiny, and much smaller than solar thermal, and of course wind. So it might, it sort of, I thought that was kind of interesting, that slide, just to see how circumstances change and how the industry trends change, in a space of 9 or 10 years. So there's the RECs created by water heater type. RECs, of course, gone now, there's TCs. And so you've got your RECs, you've got your commercial, that's the commercial there, then you've got domestic, and you've got solar water heaters, which were the dominant product back at that time. So where are we at today? So I made some inquiries with some of the companies that I've had some associations with, and I asked them if they would provide me with a few slides. So I sort of picked and chose a few that I thought would be interesting to the group here. So this one is Reclaim Energy. They're using a CO2-based heat pump water heater that is actually a Mitsubishi Heavy Industries heat pump water heater. Now, the history of the CO2 heat pump water heaters is really interesting, and I went actually to Japan back in 2002, around that time, and had a look at some that were being sold in Japan. So they've been around for a long time, and it's surprising that they've taken this long to get to Australia. But there are some issues with CO2. It's very, very high pressures, and which puts a lot of wear and tear on the refrigeration system, as you probably can imagine. But it does have extremely high COPs, and I've got a case study and a bit more information on it. So, unlike the Quantum system, it uses a heat exchanger, and so basically it's pumping water through the heat exchanger from the tank. Now, I spoke to the guys at Reclaim, and there's been a lot of issues in the past with heat exchangers getting scaling. Once they get scaling, they can't get rid of the heat, and then of course the refrigeration system overheats, compressors overheat, and you've got a warranty problem. So, but he was telling me, no, it's not an issue. We've got really high pressures and this and that, and so I believed him, and I think obviously the Japanese are brilliant engineers, so I'm sure that it's an amazing system, and I really look forward to hearing more about it over time. The CO2 refrigerant, if you look on this little chart, you can see that they're anticipating a COP of 5.1. So I'm sure everyone here would know what COP is. Anybody not? Yep.
A lot of people don't.
Okay. So basically COP is your coefficient of performance. So it's the amount of energy effectively you're accumulating from the environment and giving to the water. So if you've got a COP of 5, you've got a 1 horse system, 1 kilowatt system, you're putting 5 kilowatts of energy into the water. So it's equivalent of a 5 kilowatt heating element, even though it's only drawing a single kilowatt. And the reason it can do that is that it's extracting heat, energy from the air or from the sun. So it's the same principle used in reverse cycle heating, which typically, you've got a COP of 3 or so. I can go through that a bit more if someone wants me to. But I think we'll just move on for the moment. So Edson, we actually sold them some technology after we sold Siddons SolarStream some years ago. And they've done a lot of R&D. They're a really interesting company. They've come from commercial hot water. They do a lot of, traditionally they'll do a lot of sort of pre-configured systems using big boilers, and they'd manufacture their own tanks, and really innovative little company down in Melbourne. So what they're doing at the moment, they're doing heat recovery systems from chillers. They've got some R&D wrapped around innovation with dairies and other wineries and other industry sectors. They're involved in swimming pools. They're looking at new designs for heat pumps that are more efficient, and they're developing packages and solutions around heat pumps and solar PV. So the idea of heat pumps and solar PV not working in competition but working together will be the focus of the rest of my presentation, give or take a few slides here and there. So I personally think that there's a really good alignment between what you can do with solar PV and what you can do with heat pumps. Solar PV, of course, has a very good correlation with HVAC. So when your air conditioning loads are high, you're getting optimum efficiency from the sun. But in many cases, you're exporting energy back to the grid. And heat pumps, you can actually think about like you think about batteries, except they're cheaper to install and they actually reduce a hell of a lot more energy. So that'll be the thrust of what I'm talking about today. So there's a number of big international companies in the heat pump water heating space, apart from Mitsubishi, and I only mentioned one here today, Stiebel Eltron. And I'm going to come back to this particular design a bit later, but when I was doing my quantum water heaters, we had a water-sourced heat pump as well. And we did the Raffles Hotel in Singapore, we did Crown Plaza in Singapore, we did Navy bases, Army bases here in Australia. We did a whole bunch of big commercial stuff using our quantum water heaters and basically just installing them with equal flow manifolds. One of the installations we did was using a heat exchanger in the actual compressor assembly. So I might actually just go back. Actually, don't worry, I'll go forward and I'll come to that. But basically, instead of using a fin coil, you had a heat exchanger in there. And what we did is hooked into the chiller water in this big hotel in Singapore. And the system worked brilliantly until all the impurities in the water that was running through the chillers started scaling up the heat exchanger. Then gradually, one by one, all these bloody heat pump water heaters started failing. In the end, we had to pull out all the heat exchangers and put fin coils in. It cost me a bit of money. But I'm going to come to this idea in a minute, and we'll play with this later a little bit. So I've just got a couple of hypotheticals, and I've got some real life case studies where we're looking at heat pump water heaters and we're looking at photovoltaic power. So if you go to any hotel in the outback in Australia, in country, anywhere, you look in their backyard and they have heaps of these quantum water heaters there. They're all over the place, caravan parks, you know. So this system here was over 10 years old, and I actually stayed in this motel. I was passing through, and I went and had inspected them, and had a chat to the owner, and I took a photo. So I had the photo. I thought, oh well, I'll use that in my presentation today. So this is typically how you did it. So you have 5 heat pumps on an equal flow manifold, and they're all kind of plug and play systems. They can produce 1,000 litres each, so 5,000 in total. And the idea that I'm going to be developing a bit more is to use these as a bank so you can run them during the middle of the day. So instead of running them at night, run them in the middle of the day, where you've got photovoltaic power being generated. So instead of exporting all that power back to the grid, in many cases there will be times where you're exporting back to the grid, and so you can run the heat pumps during that time. And there's some probably people here now who are involved with controllers and electronics, and there's some amazing electronics that are wrapped around that kind of time of use space. And so it's with a smart system you can actually monitor when the heat pump will come on, and you can maximise its efficiency and its cost of running. So in this example, this is a typical curve. You've got your solar output there, and you can see the energy being consumed in the building, and you can see that obviously some of that's going back to the grid. Okay. So in the other bar chart, you can see that, what is it there, 115 or 20 kilowatt hours of energy being produced a day, and 30 or 50 kilowatt hours is being exported back to the grid on average. So what does that mean? Well, there's an opportunity to use energy from the sun to run the quantum water heaters or the heat pump water heaters or whatever the actual product you're running is. So what that will actually do is reduce the load at night. So you will see that curve coming down at night. It'll come, the actual amount going to the grid will be reduced, and there'll be a small increase in the load during the day, which is, if you're running PV systems, that's a better configuration to have. So far, it's been kind of hypothetical. So I've got a couple of case studies here. So Reclaim Energy, we spoke about their heat pump water heater earlier, and they've provided me this slide. So over a 24-hour period, you can see that an electric water heater will turn on and heat up the tank and turn off. It's governed by a pretty basic thermostat control, so it's either turning on or turning off. There's nothing particularly smart about it. So in this case, they decided to move away from electric off-peak and daylight heating and move to a heat pump water heater. And you can see the heat pump water heater is operating in the middle of the day when you're getting a good chunk of power from your solar PV. And you can look at some of the results they're getting, 83% power reduction or energy saving. Before the heat pump, 14 kilowatt hours a day. After the heat pump, 2.4 kilowatt hours a day. Okay, so that's a small domestic system, but when you start multiplying those numbers out, you can start thinking about commercial systems, and then you can really, if you've got a 100 kilowatt solar PV system and you're exporting 30 kilowatts of energy back to the grid, why not use that energy to make, 3,000-4,000 litres of hot water? Have it in storage, right? So that's sort of the idea, if you like. So you can see their savings by running a heat pump. They're fairly substantial. But the savings, if you run the heat pump during the middle of the day using solar PV are going to be greater because what's your export? Around 8 cents, something like that. On most commercial buildings, small commercial, you're going to be paying 22 cents a kilowatt hour. So instead of running the heat pump using power from the grid at 22 cents a kilowatt hour, you're effectively getting it for 8 cents a kilowatt hour, plus you're running the heat pump 80% efficiently, right? So you've got an 80% saving, and then you've got about a 60% saving on the actual tariff. So these numbers don't reflect that, but when you actually start thinking those numbers through, they're really big savings. So in this case study, the average daily hot water demand in terms of kilowatt hours has dropped from 14 to 2.4 by putting in this small domestic heat pump water heater. And again, I think the people here would be more interested probably in commercial. So multiply those numbers out and then you can actually get some pretty big numbers. If you think about applications, hotels, wineries, food processing, restaurants, supermarkets, all these kind of businesses are using a lot of power and they're using a lot of hot water. So where you've got that amalgamation of requirement, then this solution is actually a really, really strong one. So I'm almost finished my presentation today and I want to just throw something out to the audience. So I thought, here's an idea, and I'll be interested to make this a bit more interactive. So I'm interested to hear what you guys think about my idea. So, PV, as probably everyone here knows, works more efficiently when it's cold. So, and a heat pump doesn't need extreme temperature to work efficiently. Why not use a water source heat pump and something like traditional solar pool heating plastic tube? Okay? So the way it would work is that you'd have a closed loop going from the heat pump up to the heat exchanger and back. And that solar collector on the roof there is actually getting cold because it's effectively an evaporator for the heat pump. So the heat pump has a cold side, just like you would do with a refrigerator, and you've got a hot side. So absorbing heat and the surface gets cold, expending heat and the surface gets hot. That's effectively how a heat pump works. Now, if we were to put some sort of design together that could be installed underneath the solar PV panels, in summer there's a significant amount of cooling that can be applied to those panels if the panels were designed with enough room so that air can get under there and there was no nuts and bolts cutting into the plastic, and there was enough, the design had enough surface area so that the solar collector could absorb heat effectively, then it could be a pretty good idea. And I thought to myself, okay, well, what's going to happen in winter? The panels are going to get really cold. Are they going to get too cold? I thought, okay. Well, then I thought, well, hang on, it's only plastic, right? Why not put some in the roof? You just have a certain little control. In winter, this becomes a heat exchanger in the roof. Now you could put the thing vertically or horizontally, with drip trays or whatever. Let's get some engineers or the university or someone to sit down and actually work on the design, work out all these angles, and it could be a really simple but effective solution. And as a salesman and someone that's worked in R&D and someone who's worked in consulting, I've always noticed that the simple solutions are always the best. Over-engineered solutions, they're hard to sell, they're hard to maintain, So I thought, this looks pretty simple. So guys, this is my presentation.